From EE Tech Media and All About Circuits, this is Moore's Lobby. I'm your host, Daniel Bogdanoff. Today in the lobby, I'm joined by Jack Kang, the Senior Vice President of Business Development and Customer Experience at SiFive. He has over 20 patents from his time as a CPU designer and is here to dig into RISC-V. SiFive was founded by the inventors of RISC-V, and Jack was on SiFive's founding team, so we're in very good hands for today's discussion, and I'm really excited to dig into this more. This episode is adapted from an Industry Tech Days keynote, so it's kind of like a RISP, reduced instruction set podcast. Jack, thanks for being here today.
Happy to be here, really excited. Glad to be talking with you.
What first got you excited about technology and engineering?
Yeah, it's kind of an interesting question because I can't remember a time when I guess I wasn't interested in technology and engineering. I think growing up, it was sort of just the de facto thing that one should do. My dad was an electrical engineer before he moved into the business side, and it was just kind of expected. Hey, that's a good thing to do, and I, was never bad at it. I was good at math and sciences, so it was just very natural and easy. And
so when you went to go to college, you just kind of knew electrical engineering. How did you end up at Berkeley?
Yeah, so I grew up in the Bay Area. In high school here, knowing that going to college, I wanted to major, essentially in engineering, kind of electrical engineering. WE was kind of the baseline, but computer science was also very interesting. So, Berkeley had one of the EECS program, famously electrical engineering and computer science, where you could do both. And that was one of the kind of really appealing things about it. Obviously, it's also a very, top university. So, and they'll say, you're very competitive, right? Oh, I want to get into a really good one. So getting into one that, both met hey, it's a quote unquote top university. I think you learn later on, it's, maybe not as important, but, as a high school, it's a top university. But it really fit what I wanted to do. It did the electrical engineering and computer science. So yeah, going in, and that was one of those things where at Berkeley, you had to apply into that major going in. So you apply, as a senior to enroll into the College of Engineering, into electrical engineering, computer science. So it wasn't like a undecided and then you go. So in this case, the fact that was kind of the path that was already set made it pretty easy to do that. And of course, once accepted to go.
We're going to talk a lot about RISC-V today. Do you recall during your undergrad running across the creators of RISC-V?
So sort of, but not exactly. So, if you the creators, the inventors of RISC-V, who started SiFive, was Professor Sanovich, Yunsub Lee, and Andrew Waterman. So Yunsub and Andrew actually went to Berkeley a little bit after me. And while I was there, it was during Professor Sanovich. I saw his name because he was sort of in the Berkeley meeting, but he was off at MIT teaching during that time. But just going back, when I started school, I mentioned earlier, it was electrical engineering, computer science, but that's a very broad spectrum. And one of the really nice things about the Berkeley curriculum was you could pick whatever you want. So I learned, everything from, how to fabricate a transistor, to analog design, to digital design, to CPUs, to programming and OSs, compilers, and everything up to graph, like the entire stack. They did a really, really fantastic job, really, at Berkeley, letting you learn and pick sort of whatever you wanted, communication, signal systems, all that stuff. But what I found out was, it turned out I was actually pretty good and had a lot of interest in CPU design, CPU architecture design. So back then, of course, RISC-V was not invented yet. So we would learn based on the MIPS instruction set. That's what the book was written on. And when I was in school, this was, the very early 2000s. They were just starting to introduce FPGAs into the classrooms. So into the undergraduate classrooms at Berkeley, they would actually say, okay, well, now you will actually go build a CPU. Because it's one thing, I tell people about CPU designs, and nothing, it sounds really hard and it's really like, how would you ever build something? And then they teach you in class and they show you the book. You're like, oh, that's really easy. Okay, that's pretty simple. But then you go to the lab and you actually try to build it, and you're like, oh, this is really, really hard. So at Berkeley, they like, they give you the whole thing, and they don't give you much guidance. So they're like, okay, go to the lab, go build it, and go put it on an FPGA. That's literally what they tell you. They don't even tell you what an FPGA is. They're like, you go figure that out. Yeah, do you need to go use Xilinx tools? You figure that out. And I think that's the Berkeley, like, you guys go figure it out on your own, whether through tribal knowledge or, remember back then, the internet was sort of just there. So it wasn't like you just go to the internet and find stuff. Okay, this is not now. This was, 25 years ago. There's some stuff. So anyways, I was part of the first class that actually implemented the CPU onto an FPGA as an undergrad. I think the number of hours that they thought we needed to spend on the project was underestimated by like 3x. So lots of late night. So basically afterwards, that class was over. It was a spring semester class. Then during the summer, I was an undergrad and I was looking for, some sort of internship or study thing or something to work with somebody. And the most, famous professor, one of the most famous professors, besides Dave Patterson, was at UC Berkeley. He's actually ends up being the fourth inventor of RISC-V. But he reached out to me out of the blue. I wasn't even I'm not even at the level where I can go ask him for something. He reached out to me out of the blue, say, hey, how would you like a summer job to help me revamp this course and be a TA and do all this stuff? And I was like, yeah. Oh, and I'll pay you. I was like, I would have done it for free. So I got to know Dave actually quite well because we actually, spent the summer, as an undergrad. And this is typically probably what grad students would actually do, but because of I'd gone through the class and done really well, I think as an undergrad, helped him revise the course, revise the material, and then became a TA for the next year for all the next set of computer architecture students so that they didn't have to figure out what an FPGA was by themselves, but this is actually what you do, to teach them to use it. So it ended up that got to know Dave quite well. Of course, RISC-V was not a thing. But then many years later, after the industry came back and the whole RISC-V thing, it kind of came very much full circle because it was like, yeah, all the things we talked about and the principles that you wanted. So so even though not directly, I feel like it was right there at the seed, and it was kind of like the universe kind of bringing it all back full circle, 20 years later, when it came time to do SiFive.
Well, the way you set that up makes me think you jumped right over to SiFive, but I know that's not the case. How'd you end up at Marvell?
Yeah, so after I graduated, I worked at a small company doing IP design, just, the DDR controllers and PCIe controllers, and it was a small IP company, and it was just, honestly, a little bit boring. So I had a friend who was at Marvell, connected me there. Marvell, very interestingly, at the time, back then, they were one of the very, very few companies in the world that had an ARM architecture license, which means that they were actually building ARM-based CPUs. They're building their own, right? So if you're not familiar with the ARM business model, they really have two things. One, they license you cores that they build themselves, and then the other, reserved for very few companies, especially back then, was what was called an architecture license, which meant that you were allowed to build your own design, presumably for specific purposes or power targets or capabilities that you couldn't otherwise get off the shelf from ARM. But Marvell had an ARM architecture license and a CPU team. So I actually joined that team, which if you look back, is like, if you wanted to build CPUs back then, like actually design CPUs, you really didn't have that many choices unless you went to like an Intel or AMD to build x86, or you go to ARM. That was really it. So it was really kind of lined up. Remember back in my undergrad, we were just doing computer architecture. That was kind of like my area, if you will. So kind of didn't fall in like here. Now you can do CPU design, was just a great fit. And one of those things, like, at a company like Marvell, at an ARM architecture license in a relatively small team, you actually got to build very meaningful things. Because, I also, I interviewed with Intel when I was graduating and to be a CPU designer, and like, yeah, but you can design this tiny block. You design this one tiny block that goes in the whole thing. Like that's versus, you having to be able to do more. So I was at Marvell. So from day one, even though it was an ARM architecture license, it was really developing cores that had to be better than ARM cores. Because otherwise, why would you build your own, right? Because Marvell could just use his license off shelf. So
at a huge cost.
Yeah. You're spending the cost, right? And then also the customers are like, well, why should I use the chip with the Marvell design ARM core instead of the quote off the shelf, normal ARM core, right? It's different. It's all this other stuff. So even back then, I had to explain to everybody, why these cores were, quote, better or differentiated versus standard ARM, which is, spoiler alert, kind of what I have to do these days at SiFive and RISC-V. But that was really, one of the things that really got me in front of a lot of different customers and a lot of different market segments and really helped my career learn because, again, I said Marvell, we had our own CPU design. And then this would go into all the different SoCs within the company. So the different groups, the networking group, the storage group. Eventually, Marvell acquired Intel Xscale. So they had the app processors, the comm processors, and tablets and cell phones and things. So all these different groups were using the internal design. So they would need somebody from the CPU team to go, can you please help come explain to the customer what's better about our design, what's different, why should we do this, all these things. So pretty soon I got a reputation inside of the different business units that like, look, if you need somebody from the CPU team, just go ask Jack, because I was still an engineer at the time, right? But they needed an engineer who could actually go talk to customers and explain it in a way. So that became a very natural, very fast transition really from, design engineer to technical marketing to then marketing to eventually they're like, hey, why don't you just join the business unit full time and do kind of this business stuff and these other things, which was always my eventual goal. I didn't have a set time frame. I was like, yeah, after X certain number of years of doing engineering, I want to go do that. So I think it kind of maybe happened faster than I would have, if you're like, map out your plan, it would have taken longer. But it just kind of naturally happened faster that way.
Can you talk a little bit? You worked on some Xbox Kinect and related projects. Can you tell me a bit about how that happened and how that shapes your future a little bit?
Yeah, I would say the Xbox Kinect would be what I would call the my big break, right? If people talk about, what are the things in your career that really kind of affected it in a positive way. So this is the Microsoft Xbox 360. They had this thing called the Kinect, which was like the first thing that would like, it would be like a camera and it can, see where you are, and it made your whole body into a controller, and it was really revolutionary at the time. So when Microsoft was trying to find partners to build silicon to power this, it was a very, very secretive project because they didn't want to tell people what this was for. Because when they introduced this was going to be like change the paradigm of what was happening. So they were very secretive in terms of what this project was for. So they had very little details. But so when they came in and say, hey, we need to learn more about your products as a potential fit for this, to help us build a part for this, they were very light on the details. And then they came into Marvell for a meeting. And, at that point, I had just moved into kind of the business unit and on this, product marketing, called commercial type function. So I was the junior guy on like this function, right? So if Microsoft had come in and says, we're going to build Kinect, for Xbox, and it's going to be, 30 billion units a year and all this other stuff, like that would shoot straight to the top, right? It'd be like, top execs involved, certainly like the business unit leader, certainly the most senior product guy. It would not be like the fourth guy on the totem pole. So the only reason I got called up was that meeting came and one person was on some international business trip and one person was on PTO and somebody else was not available for some other reason. So they're like, okay, we don't know what this is. So I guess you come and you present it because you're what's left. So that was the break. But then what happened is then stuck with it, built it up. We learned more about what it was. And then, we started working with them closely and just never let go of the opportunity. And then so from engagement through building a whole ASIC for them, delivering it on time, the entire contract, that sort of everything that happened, that entire experience, which, most people take years to get. Like, can you get the chance to get that, what do they call it? From cradle to grave, I guess, from the beginning to the end. And then never let go. And then it was a big success. So then it became like, oh, okay, well then clearly Jack's pretty good at this. We can give him more responsibility. He's he can do this, right? And I think this is what I tell people, what's the difference? Like, what does good luck mean? Like I was lucky that the opportunity came to me, but I was in a position where I could take advantage of it and execute on it, right? So I think everybody has, in your career, you have certain opportunities, right? You can't control when they show up. It's just, can you take advantage of it? And, will you have enough of those so that you can demonstrate it to go? And so that, to me, was sort of the big break, because it came in, it was huge. It ended up being like the fastest selling consumer device of all time. So it set all sorts of sales records. It was highly visible throughout the entire company. So the credibility that I built with my colleagues and coworkers and everything else was like not instantly, it was a 1-year project, but then it jumped up a lot, right? So it didn't matter anymore after that, they have a decade plus of experience on me or whatever else. It was just like, you're it's like a peer. You can do this. Great. Here's more things. And that's basically what led to more and more opportunities, more and more responsibilities. And, you go from there.
So from there, you then, speaking of opportunities, went to Nvidia and spent some time there, I understand?
Yeah. So, so after I moved on to the, Kinect project, I was already on the commercial side, was there for a few more years. It was very, very interesting years. Those were the beginning of, Android. We were in mobile, got to see all of that, got to see what happened to BlackBerry. Marvell was one of the main suppliers into BlackBerry. I was there in the room with the BlackBerry CEO the day after the iPhone first launched, the very first iPhone, the original iPhone, and to see their reaction, which was one of excitement, because they can say like, hey, this is going to be great, because this is going to show the world why everybody needs a smartphone. And he was so right and also wrong at the same time, because it showed the world why they need a smartphone. But, they thought that meant that for them, they would expand. But there's a few things that happened there that we won't quite get into. So then after, a while, and, I was working directly with Wei and Sahat, the original founders of Marvell. And there's, like I said, it's a fantastic learning experience. The ability to do all these different things and get all these reps. I'm really grateful for my time there. But it was time to do something else. So then that's when I went to Nvidia. I was on the application processor side, responsible for Tegra. And those were kind of the last days when Tegra was still trying to go into kind of the mobile space before everything shifted to AI and accordingly. So I was at Nvidia, and kind of the big thing I worked on at Nvidia was the Nintendo Switch design. So again, this is another one of those, like, I guess you kind of get lucky and be presented the opportunity to go in there. So the part Tegra that we had became the basis for the Nintendo Switch design, which is obviously hugely successful. Gone through all of that, and I actually tell people this is like one of the first time that Mario was rendered legally on an NVIDIA GPU. Legally, right? Of course, there's all sorts of stuff. Because NVIDIA never actually sold directly to Nintendo before. So this was a pretty big thing. It ended up being massive volume units, big success for Nintendo, big success for NVIDIA. That was basically my project. I wouldn't call it a project. That's basically what I did at NVIDIA, was the Switch designs and a couple of generations of that while I was there.
What was it like jumping into product design that has such intense fandom and following and pretty technical audience in a lot of cases?
Yeah, I think, it's actually one of those things where, because these programs that you work on, they take a few years, right? So I knew, for example, that Nintendo was going to have a Switch product, which meant that you can have a portable console and you can do this and you can do that. And we're working through to solve all of these problems together in terms of how do you get the performance up? How do you deal with the thermals? And you're dealing with all of these day-to-day problems, knowing that this end result, that people are going to just love it and it's going to be so excited for it. But I think what happens is that when it launches, all your friends, even randomly, they're like, "Oh, that's so cool! It does this, it does that," and then you're kind of like, "Yeah, I knew that for like a year." So it's almost like kind of like it's not that cool because you worked on it through all the problems and everything.
Yeah.
But then you realize that it was actually really meaningful because you get random people asking you stuff. I got random people on Twitter asking me for like inside info on Nintendo and Switch and all these other things, which of course I can't tell them, but it's like, oh, there's this massive fandom out there. And it does make it kind of, more meaningful when you're really pushing to solve the problem, to be like, yeah, let's actually solve it. Let's not just give up and be like, well, you just can't do that. Because there is that, if you solve it, it'll be great. And I think the other thing to me is about, the really good product companies in the world. And I put Nintendo up there, like they really know what they're trying to build and why they're building it. Okay. Like they really know, like as an example, we had this whole discussion. I think it's probably okay. So now we had this whole discussion of like, should the Switch support like Netflix, right? Because clearly the chip and the platform, it can support Netflix and we had all sorts of stuff. But it would have been more software work. And then, I assumed that of course they're going to want to do it because, technology, like all the features that you get, of course you put it in there. And they're like, no, we don't want that. This is an entertainment, this is a game playing device. We're going to focus on the games and the experience. It's not here to stream Netflix. There's plenty of other devices that people have that stream Netflix. So no, we're not going to do that. Maybe in the future, they weren't rolling out forever, but it's like, we're not doing that right now. And it was just such a interesting way of looking at it that makes total sense, right? I explain it. It makes total sense.
Oh, yeah.
Right now, I explain it. It's like, of course, obviously, right? But we go to the meeting, it's like, oh yeah, okay, we better tell them about the plan and how we can support Netflix. It just was like assumed that like this was gonna need to be there. We're gonna have to port this software, we make this security thing, but it's like no, we're focused on the games. So I think it was really valuable lesson. I take it as like, okay, what does it actually mean to be a product company, to build a product, to know what you're building it for, right? And I think this is we're all guilty of it. It's very, very easy, especially as an engineer. Engineer might say like, well, we could do it. We can add more to the checkboxes, and sometimes you don't need more to the checkboxes. There's costs to adding things to the checkbox that manifests itself that in ways you don't know right away. So I think that's a really valuable lesson that I think, Nintendo did a good job. And, certainly Nvidia has, we've all seen what they've done. Very disciplined in that, and very disciplined in knowing where's the value, what are you creating, and focusing on that. So
I'm interested to hear how you decided to go from very big, huge companies to being almost employee number 5, employee number 6 at SiFive, which had to be an entirely different environment. Well, what was going through your mind when you started having conversations with them about coming on board?
Yeah, no, that's a great question. So there's kind of two parts to this. And I guess I would tell everybody, who's like looking at stars. So the first thing that came to mind was like, when I first heard about what they were doing with RISC-V, it actually solved the problem that I had in my head that I had been stewing with for years, both like at Marvell and at Nvidia and all of this, this time. And then that was when we chip companies and we work with the customers, it was very difficult to work with. Customers would say, hey, can I please use your chip to do this thing that's kind of slightly different? And they're like, we'd have to go ask them like, okay, well, what's your volume and when are you going to ship and all this other stuff. And the reason we had to ask them that is because the software support needed to get them to production was so high that it was very expensive. Like, okay, well, then we're going to have to tweak this. We're going to do this. We do all software stuff. And I was like, well, why do we have to do all the software stuff? I was like, well, because the drivers that we give them are like black boxed. I was like, well, why don't we just give them the source of the drivers and then let them tweak it? It's like, oh, no, we can't do that. If we did that, then they'll know all the secrets of all the things that we're doing. Really, they'll know all the secrets of this multi-$100 million chip that we built and all like that would reveal all of that. But the hardware mindset of that these things have to be like closed to get the value out of it was so difficult to break. And then so it didn't really matter how smart you were as a customer, how much energy you wanted to do. If the guy didn't want to support you, you couldn't do it. So I had this notion in my mind of like, can we make hardware more accessible and more open and more just, like more open sourcey, like how software has done things, right? Where, Linux is open source. Lots of people make money using Linux. It doesn't mean that you give, but like that concept of openness that exists in software just did not exist in hardware. And I was like, how do we bring that in to hardware? And then I got stuck because of the chicken and egg problem. It was like, well, you have to have enough hardware things that people care about so then they contribute to it so that it then lives and it keeps going. So it was like this chicken and egg of like, if you want hardware to be more open, how do you do that? And I couldn't solve that. It bothered me. I couldn't solve that. So when I first basically came across SiFive, it was a recruiter. They paid recruiter. Explained the thing, and I was like, oh, that's it. That's the thing that breaks this chicken and egg. This is enough of a thing that it's going to take off and become those things, right? So first the idea, and then the momentum behind the idea to me felt like something that was going to solve actual problem. And then they were talking about the company and the technology and its RISC-V and its CPU, and it came from Berkeley, and they need help figuring out the commercial side of how do you do this. So you need somebody who knows CPUs, who's actually done commercial stuff in this space with big customers, has that credibility. And I was like, plus I went to Berkeley and I know CPUs and all sorts of stuff. So honestly, I was not trying to be arrogant at all in the first meeting, but the guy called me, right, and explained his stuff. I was like, okay, well, I don't know if this is going to work out. Like, I really don't know. But based on what you described, you're not going to find anybody more qualified than me. Because like, you go through all the things, and you went through my background of what I've done. It's like almost like a perfect fit. Plus, I was of similar age to like the founders, right? So there's this connection that existed also. So when I first met Krista, Yansup, and Andrew, the first thing I said to them was like, let me tell you what my idea is, because I don't want to be influenced by you. And you tell me if it fits what you guys are thinking, right? So I went through, what I thought RISC-V could be and why I could do all stuff. And they're like, yeah, that's exactly it. So that just made it a very, very natural fit. And we could talk through what all of those things are. That's kind of what we've been doing. So then it just became okay, do you want to go from very nice, big company, my job at Nvidia was going great, right? We had the switch programs, right? Nobody bothered me. I could pretty much do, free reign to get involved in other things or not, do kind of whatever I want, keep Nintendo happy. It's all good. Everything else is kind of bonus, very, honestly, very comfortable. But to me, it's like, well, do you want to go do that for a startup? That obviously is very risky. Who knows what will happen? And at the end, you have to ask yourself, it's like, well, if you go do this startup thing and it doesn't work, and 2 years from now it doesn't work, could you come get your old job back or a similar job to that? And the answer is like, yeah, well, yeah, of course I can do that. It's like, well, okay, if you have confidence that you can do that, then what are you really risking? Okay, you're risking 2 years of lower salary, right? Because obviously startup, right? 2 years of cash flow. Could you afford that? Like, okay, you can afford that. Okay, well then just decide, right? So that's really how kind of I looked at it. So then obviously I joined, and yes, it was a much different experience. I remember the first week I joined, our office was in San Francisco, which first was weird. I don't know why you put a startup in San Francisco. That's hardware. But anyway, we were in San Francisco in this tiny room, no air conditioning, only a window that opened like 6 inches. And it was like this heat wave. It was like the hottest summer in San Francisco in like 100 years or something. It was so crazy, ridiculously hot heat wave, but there was no air conditioning. And my friend at Nvidia called me that day. And he was like, how's it going? I was like, there's no air conditioning. He's like, there's no air conditioning. You got to come back. I was like, yeah. We'll go get some ice cream. That's what we're going to do instead.
Nvidia knows how to deal with thermals, is what you're saying.
That's right.
So tell me a little bit about RISC-V and SiFive and how the two play together and kind of what the point of it all is.
Yeah, so I think when I joined and we started the company, we thought that RISC-V was very important, and that RISC-V would fundamentally change the semiconductor industry. I mentioned some of the things earlier, like bring kind of the open source ideas or open standards, but those are all like directional things, right? So really at the beginning at SiFive, like most startups, you're not 100% sure what your business model is, right? Exactly how do you go to market? We knew that we had some, pretty interesting underlying technology that could let us build things quicker, whether they were cores or whether they were chips. But we knew there's something around, RISC-V that was going to be really important to the market. So the early few, months, I would say, a lot of time was spent educating the industry. What is RISC-V? Like, what is RISC-V and why does it matter? And this is kind of interesting at that time because I can honestly say that the more somebody knew about computer architecture back then, the more pessimistic they were. They'd be like, RISC-V, wait, why do you need a new ISA? That's like crazy. We don't need a new one. We haven't had a new one. The world is this. Why would you start a new one? Versus some folks maybe were not as familiar with ISA. So like, oh, this makes sense. Eventually we converted everybody, but that's kind of interesting. If you ask what's the early industry reaction was, like the more you knew about it, the more like pessimistic you were. Like, why would you create a new one? Until, we explained the benefits of like, having an open standard, multiple people can contribute to it, broaden the ecosystem. You can then have your own customizations, you can have your own configurations, you can do things in a way that's not reliant on a single proprietary vendor. And then you just really point out that, the whole world, or when I say world, I mean like our technology world. Our technology world is all built on open standards. Ethernet is an open standard, Wi-Fi is an open standard, even, 5G is open standard. These are all standards that people can compete on, and they build things, right? Anybody can build Ethernet stuff, but Cisco makes the most money building Ethernet things, right? Because they do things. So open standards actually make sense. And the aberration was the CPU ISA was the only one that wasn't an open standard, where you only had x86 and ARM, which everything else was an open standard. So then people started realizing that. And then sort of at the same time, this started happening. Some of the early adopters, they were, oh yeah, okay, we want to start doing this RISC-V thing, but actually we would like you to do it. So we didn't start off necessarily intending to be a RISC-V IP provider. Certainly that was one possible thing, but part of this was, hey, well, it's an open standard. Lots of people can build RISC-V. Like maybe we should be building, helping build chips and helping do things related to that. But customers kept asking us, can you please build RISC-V cores? Because even though it's an open standard, it's still hard to build a CPU. I mentioned earlier, in theory it's easy, and actually it's very hard. And then you want to build commercially viable CPUs, and then you want to hit different performance points, different power targets, different area targets. You will need your CPU to not just be a CPU, but you need it to work with debug tools. That means you need to work with third-party vendors. You need to be able to integrate it into SoCs, and what do the commercial tools expect? All of these things that like add up is actually quite a lot of stuff. So people are like, hey, can you guys please just help us build our cores? So then it sort of evolved pretty quickly, because the technology that the company was founded on was RISC-V technology, and then the other one was the ability to, I would say, configure and do iterations very quickly, which lets us find optimal design points, but also design cores much faster to hit different points. There's a lot more reusability in the SiFive methodology, much more of a software approach to building hardware that lets us, we believe, build things much faster, much more efficiently. So if you look at the amount of products that we've released in the 7 years, it's actually really, really significant. But so then this became kind of the model where customers would work with us to get their RISC-V cores. They could configure it in certain ways. We had configurator built in so people can tweak things and do things of that for their application. And then we help them with the software. And then this just kind of grew from there, right? And then as more people start building RISC-V, it's kind of grown. That's the momentum of it. But yeah, the early times was just explaining to everybody like what is RISC-V and why should we care.
Yeah, I remember being blown away. I have a RISC-V, dev board over here, like an FPGA with a core. And normally when I would do any sort of FPGA work, you have to you write the check to the vendors and get the software and do the thing. But this was an entirely open source tool chain, start to finish. And I got as far as like flashing an LED, and then I went on to another project. But like the ability to do it all from open source, open hardware platforms was incredible.
Yeah. No, I think it sits very well. Just go back to software, like you can have certain things that are open source, which lets lots of people play with stuff, which lets lots of people innovate, which means there's a lot of teachings at schools and universities and research projects, and all the PhD students are basically all doing RISC-V projects. But you still have very viable commercial side, right? It doesn't mean that everything you do is like open access and available. Like you can still have proprietary implementations, which are important. You can still have things that are secret. Like you can still do all of these things. It's just built on an open standard, gives you all of these choices. And then now all of these ways that people can interact with RISC-V all contribute to the broader RISC-V ecosystem. So we have PhD students contributing to the open source tools. We have individual, maybe hobbyists who are just interested in stuff. They're able to do things and it's just for fun. Right? But maybe that for fun turns into a commercial program. Maybe that turns into an open source contribution. Maybe that turns into an idea for future enhancements to RISC-V. But all these things work together. And this is where, if I look at the RISC-V ecosystem, it's like, we talk about the future RISC-V is inevitable. This is what we're talking about, because everybody's going to be working on this for their own purposes, but collectively too, right? Which is much different than any other proprietary ecosystem, because if you're in a proprietary ecosystem, at the end of the day, a certain percentage of what you're doing is benefiting the proprietor of the proprietary thing. Here, it's benefiting the whole. You can take out of it what you want. You can partner with the other companies, the other contributors, how you want. And I think this is a big mindset change in the hardware industry, and people rapidly adopting it. And we've seen the success of this on the software side of what happens when this happens.
We'll be back with Jack in a moment, but keynote speakers for Industry Tech Days are sponsored by Mouser Electronics. As your design fulfillment distributor, Mouser is your authorized source for millions of components from thousands of leading brands. Come discover, design, develop. And now, back to Jack Kang, SiFive's Senior Vice President of Business Development and Customer Experience. So if you'll let me nerd out a little bit on RISC-V, what are some advantages, like operationally, that RISC-V has over x86 or ARM? Like, are there different instructions somehow, or what does that kind of look like on a technical level?
Yeah, so I think there's a fundamental level which you sort of talked about, but I think you're asking about like the technical level, right? And one of the very nice technical things about RISC-V was, frankly, it's just new. So when you design something that's new and modern, you get to benefit from all the, whether they're mistakes or things that made sense at the time that no longer make sense, that are like baggage in old designs. You don't need to carry that with you. So let me give you an example. x86, you pull up the instruction ISA manual. The first instruction that pops up is like AAA, which is like add ASCII addition or something. It's like a addition function for like ASCII code characters, which it doesn't make any sense anymore in any modern compute system. But because that's part of x86, because when it was invented back then, they had a specific use case for it. It's there. But now you have to carry that baggage with you. So when you start carrying that and you carry baggage for like 30 years, 40 years, you have stuff that's just in there that just weighs it down, right? Like not literally, because these are transistors, but like it makes it bigger. You have to implement it. It just consumes power. It's just there, right? So having that clean slate design lets you kind of avoid all that and lets you do things that are very, directed and works well with modern programming, how people are using it modernly, the latest things that compilers can do, right? A lot of things in in ISA land were done maybe back in a time when there was more hand coding and the compilers weren't as good. So you do a few things there that make hand coding easier, but now it doesn't actually make any sense. Or things that, are easy for certain types of implementations are not easy to implement when you get to these very complex out of order machines, multi-core, multi-cluster, which actually makes the machine more complicated than it has to be. So time and time again in kind of CPU history, it's always been sort of, you revert back to, actually the whole RISC style computing of simplicity actually ends up being the most efficient. So you have to be very careful what you add on to. So RISC-V fundamentally has the benefit of being new. So that's like level one, right? So if you look at the amount of baggage that's in x86, is certainly more than the amount of baggage that's in ARM, which is, there's no baggage in RISC-V. Now, maybe 30 years from now, RISC-6 will show up and RISC-6 will be like, hey, see, look, RISC-V, they add these things and maybe it's not good. We don't know, but that's part of it. And then the other really key part of the technical implementation and capabilities is it was designed from the beginning to be modular and to expand. So it was designed to kind of let things expand, to reserve certain spaces for people to do customization. So you can do these things in a way that's sort of additive and doesn't block into each other, right? So there's like a 32-bit and 64-bit RISC-V right now. There's already a 128-bit version that's like defined and ready to go. Nobody's going to implement one right now because it doesn't make any sense, but it's there. So like when you get there, it's kind of like a smooth transition. It's not going to like overwrite your old stuff and force you to throw away your software stacks and the things of that nature. So it's kind of designed with that in mind and that extensibility. And then now that it's the standard is being written or being maintained rather by RISC-V International, it's a coalition of companies and member companies who are involved in this. So we also get to pull in the best minds from everybody. Talk about like security capabilities and features that are what important. It's not just who are the best people that SiFive could hire, or who are the best people that this other company could hire. We benefit from that collective knowledge as well, which is a bit different. But that's kind of the technical thing. But then going back to the larger item, which is the fact that it is an open standard, which means anybody can use it and take it. That is like the big shift. Once you have that, then you pull everybody in. They can implement all these different models, and you put more energy into making it technically better. So moving that from a proprietary, one company owns it, and they might be motivated to change things for commercial reasons and not just technical reasons. Because how do I sell you something new, or I got to make it different, even if it need to be different?
Yeah.
Because you already paid for this, so how do I make you pay for that? It has to be different, right? Because at the end of the day, like our customers, they have to decide, do I want to use ARM or do I want to use SiFive? And they're looking at our products. They're looking at ARM products. ARM's a very successful company. I wish them the best. Hope they have a giant IPO. They have been in this business for many years. Their products are very good. So when the customer says, I'm going to switch out this ARM core for your SiFive core, well, our SiFive core better be very competitive. It better be better in power, better in area, better in performance. And one of the things that we found, for where we compete with ARM, like we do bring that. We bring products that have better compute density, so for the same performance, you can achieve it at lower power and lower area, right? Because the product at the end has to be better too. You can't just be like, oh, it's nice. This movement is great. I want to be part of it. But they have to compete, right? If they use our SiFive core and they're competing in the market against a competitor who's using our core, like if it's not better, they don't win, right? It doesn't really matter the nicety.
Just so I understand properly, or so I understand correctly, there's a RISC-V layer, which is kind of the open source technology protocol that has the consortium, the standard. Yes, and then SiFive on top is building their own set of IP and potentially licensing that out to other folks.
That's right. So the RISC-V ISA, what I call the standard, that's really just a standard set of instructions, manuals, like this is what you have to do to be compliant. Because at its heart, the ISA is really just the contract between hardware and software. So hardware, you shall do this. So therefore software, you can write like that. So the standard is just there specified out. And the RISC-V standard is an open standard, which is anybody can freely use it, but you have to implement your actual implementations on there. So SiFive, we implement our CPU designs, and we have some small cores and we have some big cores, and we implement different versions of it that are all compliant to the standard. But because this is an open standard, others can implement a version of the core that meets the standard, and they can release that core in open source, right? So then you have your choice of there's open source cores, there's cores from SiFive, there's cores that you build yourself. This, duplicity, this diversity of options is what gives RISC-V a lot of benefit, because now you can do all these things. You can use an open source core, you can build your own, that's secret. You can go to SiFive and you can, license one of our cores. And this also means that you can imagine, that means the world will have the most number of RISC-V cores because different companies can build it. So there's clearly going to be the most RISC-V cores in there. Now, not all of them will be useful, but there will be the most RISC-V cores. But that means you can choose the one that really fits your application. And the nice thing about RISC-V is you get what you need for all of those, and they all run the same instruction set, which means it's all the same tool chain, same tools, the same software. It's very, very nice. So go back to, the original, like, what are the technical benefits? It's like, well, I don't have a different instruction set for my microcontroller than like my big core. And now you can share your tools, you can share everything because it's all RISC-V. This is very valuable as we build these more complex systems that need, heterogeneous cores and large and small and things like that. So it's coming along at exactly the right time where people are verticalizing and need customizations, they need configurations. So, one would say it's like, oh, it's ideally suited. Oh, good job. I guess I would, not be so bold. I'd be like, you know what? The whole luck and preparation thing, it's like, look, it's successful because it came along at the right time where the world needed this came along. So boom, it happened, right? If this came 10 years earlier, maybe the world wouldn't have been ready for it. I don't know. We can never prove that. But it came right at the time when the world was going vertical, needed customization, needed all this stuff. So it fits very well. And now you have this opportunity, can you walk through that door and take advantage of, preparation and opportunity? Right. That's correct.
Yeah. Fantastic. Well, I'm sure that people who are in this space are bugging me to get to some applications here. So can we talk a little bit about security and chip security, and what are considerations and things people have to watch out for, and ways that you kind of help address some of those concerns? Because obviously with open source, anything, there's always that, initial concern of, is this safe?
Right. So I think the open source, is this safe, tends to be a little bit of a red herring, because if I say, like, if you're going to use a core from SiFive, that's not an open source core. We implemented it. We know what's in there, so, we didn't, there's no like chance for some weird actor, they stuck in some weird backdoor into your open source code base. This is a SiFive design. Now, when our customers talk to us about security and safety, like these days, it's like, how are you securing from an architecture standpoint? How do you secure your memories? How do you prevent side channel attacks? How do you do these things? So there's safety and security. They kind of go hand in hand. So there are certain things that exist in RISC-V from an architecture standpoint that we've worked on. So for example, WorldGuard. WorldGuard is kind of an overarching term for the security architecture for RISC-V cores. So basically, how do you protect the memory accesses? How do you make sure that the different privilege modes or privilege levels inside your CPU only have access to certain memory regions and not other memory regions? So that architecture as a whole is called WorldGuard. It was originally developed at SiFive. We've donated that to the RISC-V community to make it the RISC-V standard, because one of the important things here is we want everybody in RISC-V to be developing on the same standard. That's how the ecosystem grows. We can develop trusted execution environments on the same common base. Plus, by donating it and making it openly available, everybody gets to view it. So you get to view the security architecture. It's not security by hiding things, by being secret, right? That really doesn't work. If it's open and secure, that's the most secure, right? So everybody in the world gets to look at it. Okay, yeah, you actually implement this, do this, it actually works. It's secure. So that's kind of, one of the things that we do, leading this space and driving it forward is like these important things. We want to make sure that, we want to grow the whole RISC-V pie. If you look at WorldGuard, the closest comparable from ARM has TrustZone. And TrustZone was done kind of at a time when security was sort of an add-on afterwards. So it was within the limitations of the systems at the time that they added TrustZone. And trust zone basically creates two worlds, a secure world and a non-secure world. So it creates two worlds in your SoC, and they're kind of partitioned off. But it turns out, two worlds is actually not enough. You actually would want more worlds. So WorldGuard lets you create many worlds. You can have 2 worlds, you can have 4 worlds, you can have 8 worlds, you can have, depending on how much hardware you want to throw at it, you can have more worlds, and you can have more fine granular control of what you want between, this hypervisor or this trusted OS or this application, and not be able to talk to each other, versus if you only have 2 worlds, you still have to stuff them all into one of them, and then you have a lot of software control. So that actually ends up being a potential vulnerability. So this is kind of like, being able to build on top of what exists in the ecosystem lets you build sort of stronger things, I guess I would say, or, more advanced things. This is one of the benefits that we have. So this is a important area for us. And this is also one of the reasons why customers work with us, because commercially, you want somebody who's thought of this, stands behind it, and does it. There's a big difference between this and an open source core for research versus an open source core for a multi-million-dollar project.
Yeah. And what a unique position to have the inventors of RISC-V be the founders of SiFive, that there's clearly a lot of, influence and cross-pollination there.
Yes. So
can you tell me a little bit about RISC-V for automotive and how automotive vendors and designers and developers think about this, and how that might be different from someone like a Nintendo or one of your, one of the companies that you've worked with formerly?
Yeah, I think automotive is one of the most exciting markets that's happening right now, both in the world, but also especially for RISC-V. And let me tell you why. So automotive is currently going through a generational change, right? 2 things are happening. One, we're all going to electric vehicles, right? So this means we get to redesign the car, right? We actually get to fundamentally redesign the car. This does not come along often at all, right? And at the same time, we get to all redesign the car. Autonomous driving capabilities and self-driving cars is coming. And it's not a solved problem yet, which means that we need more and more compute capability to solve this problem. So you're coming in at an exact time when people have to redesign everything anyway, because electric cars, and they need more compute because they're now trying to solve this problem. So that's like a golden intersection for a new architecture. Because one of the hardest things from a RISC-V standpoint, even though the ecosystem is growing and all this stuff, like if you go to a market that is already well established and everybody has to rewrite the software, that's a lot of work to rewrite everything, right? When it's already working, right? Am I going to rewrite all my software because it's 30% better, 40% better? It's okay. But you look at automotive, I have to rewrite my software anyway. Everything is new. I have to rewrite it anyway. So now I get to choose upon which ecosystem do I want my next 10, 15, 20, whatever number of years of automotive things to be on. And you have a fundamental choice now of, x86, ARM, and RISC-V. So if you're rewriting your software anyway, the clear choice is RISC-V, because you have vendor select choice, you have different ways to do things. As long as the products there meet or are better than ARM products or x86 products. And I think the other factor in automotive is it's an area that, relative to some of the other markets that ARM has been in, has been less, it doesn't drive as much revenue as some of their other markets. So the investment in automotive is just naturally less. So in a way, we've been able to, our products demonstrate in automotive already better than what our competitors has. So now you already have this capability to bring better hardware, and you're able to rewrite all your software anyway. It becomes a very natural landing spot. So a lot of the technologies that we're working on in terms of AI capability, our intelligence cores for, computer vision, advanced driver, self-driving cars, all those technologies intersect really quite well in an automotive space.
So one of the things that I see happening a lot in EV and just in the world overall right now is, autonomous vehicles and AI, machine learning. That's not necessarily new technology, but it's definitely being deployed and has a spotlight on it. How do AI ML engineers think about these cores and this technology?
Yeah, I think, I get asked this question a lot because people are like, what are you doing for AI, or what's your AI vertical strategy. Or so I think my view is like AI is a technology, and it's going to make its way into all of our products, into all of these. So it's not a vertical by itself, but like automotive needs AI, edge computing needs AI, our consumer devices will need AI. So what are we doing to enable that? So from a SiFive standpoint, we believe that really with AI, the key right now is making sure that you have programmability built in. The AI algorithms and what's happening in this field is moving so rapidly, right? So a few months ago, ChatGPT showed up, and now everybody's all about transformers. We need to do lots about transformers. Whereas a year ago, nobody was talking about transformers. They wanted to run their neural net engines, and how do I do my convolution nets faster? So if you build hardware that was very optimized for neural nets, you're kind of in big trouble now, because like that hardware does not run transformers very well. So how do you solve this? So our view is really, it's about the programmability and efficient programmability, and then being able to complement that with hardware that does very specific things. So as a CPU provider, our CPUs have vector capabilities in them. We have performance cores, we have certain size vectors, we have intelligence cores, which is much wider vectors. And RISC-V vectors presents a programmable way using standard RISC-V tools to program in very efficient way of moving data around. You can do your pre-processing, you can do your post-processing. You can do transformers, you can do neural net. It's not as efficient as a hardwired engine, but it lets you do that programmability. So our view is to then, in certain areas where you just need a little bit of AI, you can run it straight on the vectors. In other areas, we have an interface that lets our customers connect their hardware engines into like next to our intelligence vector cores. So then now it's closely coupled together. And what that allows is in a RISC-V programming environment, now you can control your hardware. So it's actually easier to program. But then also you can offload the things that your hardware is good at, but whatever it ends up not being good at, because there's something new that comes up or whatever, you can handle efficiently in your vector core. So you can do pre-processing, you can do post-processing, you can do data manipulation, you can hand things off, you can come back. And because it's tightly coupled, the power goes down, it saves a lot of the data transfer and things of that nature. So one example, public example, is Google actually has an exact use case with some of their TPUs where they connected their TPU to our Intelligence X280 products, connected together, and that's how they want to program their TPU and run things. So they pre-program programs. They had a talk about this about a year ago, explaining this exact use case.
It seems clear to me we're probably not going to see RISC-V in an iPhone, or if they did, they would name it something else and not tell us. Might we see an Android phone that's running off of RISC-V?
So I'm very confident that we will see an Android phone. But if you ask me when, then that's where I might need to hedge my bets a little bit in terms of when that will happen. What has happened recently that we're all very excited about is, Google has announced, tier 1 support for RISC-V in Android, which means Android will run on RISC-V. AOSP, they're committed to doing that. If you've been keeping track of some of the announcements that they've done in the last, 9 months, in terms of enabling RISC-V for AOSP, developing the NDK, SDKs for RISC-V, compatibility, CTS, CDD, all those things that are required for the full Android experience, not just AOSP, but eventually Android and Google services. All the groundwork for that is being laid out. Now, just because you have Android doesn't mean you have an Android phone. Android goes into many, many devices. But this is really, really important because now you talk about devices that use Android as a baseline. They can now support RISC-V. You can talk about things like wearables. You can talk about things like Android Auto or Android TV. These are all things that run on Android. That's not Android phone per se, but I believe all of those will happen sooner because if we look at the app ecosystem, the challenge with Android phone proper is that's where you have the full millions of apps. So how do you make sure millions of apps run on RISC-V? That takes time. That takes some technology things. That takes other stuff solve. But if you look at a wearable, there's like 50 apps on a wearable. You look at Android Auto, there's like 50 apps on Android Auto, roughly speaking, right? You can get there much faster in that space. And I think this is actually really important, for RISC-V, not selfishly. Of course, I want Android to run RISC-V, but if you look at from an Android perspective, it's good for them too, right? Because they want to run on multiple platforms. Because if Android only runs on ARM, then they're limited by what ARM produces, right? If ARM doesn't make a core for a certain segment, they don't make a core for a certain segment. So like last year, Samsung announced their new Galaxy Watch. So I think this is, in 2022. So not this year, but last year's 2022 watch. And that watch used like an A53 core or something. That A53 core was like 10 years ago, right? Because the core is 10 years old, right? Just because there hasn't been a new core for that space. That makes sense. So, okay, well, ARM still gets paid because they still got licensed that core. Samsung's still making the watch. But now if you look at what is the Android watch experience compared to maybe an Apple Watch experience, which is not using a 10-year-old core, but using a very recent core, it's very different from a power, functionality, responsiveness thing. So I think this is where competition is good because it forces everybody to keep going. You got to keep building better and better things. So I'm very excited that Android is coming for RISC-V. I'm not making any predictions on like timing because that thing takes time. It takes multiple folks from us on the core to the software to the chip vendor to the OEMs, and it's gonna be different for all the different markets that I'm predicting. I'm not saying that they're all going to happen or what time, but this just goes back to the larger trend. And because it makes sense, you need to have multiple platforms. So if you're Google Android, you want multiple platforms. That makes sense. Okay. How quickly do they get it done? That's up to them. I hope it's faster, but I think this is where the world is going, right? So it will be RISC-V. There will be a RISC-V phone. It's just, when.
Wonderful. Well, thank you so much for your time, Jack. This was really interesting and exciting for me.
Yeah. Well, thank you for having me. This was a lot of fun.
And thank you to Mouser Electronics for sponsoring this podcast. I love the potential of RISC-V, and I'm personally really excited to watch it continue to get more and more traction. If you enjoyed this episode, please let us know on the Moore's Lobby social media pages. We love getting your feedback. And if you really like this podcast, please share it with your friends and coworkers. I'm Daniel Bogdanoff. Thanks for joining me today in the lobby. I'll be back in 2 weeks with a stacked panel featuring top engineering leaders from Microchip, Endries International, and Menlo Micro.